So what are we on to now?
I think the second-hand rule.
Oh, for Flux sake. So take that home with you.
Yeah, that's good. Okay, so now we're on to gang signs and magnetic flux.
Yep. So we had this rule, and that was lovely. That was lovely.
Yeah.
Not where it stops, though.
Not where it stops, because we had the current and we had the field. Interesting about the field. In electric fields, it's measured in electric field strength.
Yep. So E.
Yeah.
Gravitational fields, you use G.
Yeah. In magnetic fields, we use flux. Obviously.
Yeah, obviously.
Yeah. M is taken, I think.
So that's capital B in equations, which we get to in a bit.
Yeah.
And it's measured in Tesla.
So let's see when we use our left-hand rule.
Yeah. So firstly, what if I have a wire
Mm-hmm.
and it's going into the board,
Right.
and the current is also going into the board because of the X.
Okay, and we know this rule, being hitchhikers, that if we do this, it goes into the board, it's going to go round clockwise.
So we can have lovely little thingy things.
Lovely little thingies, field lines there. But what if we then interfere this and superimpose another field upon it?
So if we put it in like a horseshoe magnet with
Yeah.
Nigel.
And Steve. Now, everyone hates Nigel.
And everyone loves Steve.
It's true.
So there's field lines going from Nigel to Steve.
Yep. And if we just superimpose them on top of each other, that's what it will look like. But it won't really, because there'll be a resultant magnetic field lines.
They're going to
because of
interfere
this.
with each other.
Yeah.
Enter gang sign.
Yeah. Because what we want to know is what direction of all the things are going.
Yeah. So altogether there's going to be some sort of motion or some sort of force being applied to this wire.
Yeah.
That's going to try and make it move, and it may well make it move. It depends on how fixed in place it is.
Yeah, so
we use this.
Speaking of motion, we use left-hand rule. So we have our thumb.
Thumb.
Motion.
Motion.
Yeah. We have our first finger.
Field.
First finger.
Field. Yeah.
And we have the second
finger current. Now we're not just special. Those are trying to help you remember which finger does which thing.
Yeah, and it's important that they're all at 90 degrees of each other. That's why they're like this. You will look very strange in your exam, sort of doing funky, awkward angles. With
you will look quite silly. So
everyone else, so that's fine.
So this thumb, this motion, sometimes it isn't motion. If this wire was really, really held in place, then the direction the motion would fall, there wouldn't actually be motion because it's fixed in place, but you'd still say the motion's that way.
Yeah, it's really talking about the force in newtons on the thing.
The force would cause a motion if it wasn't fixed in place.
Yeah.
So.
Then we have this, our field, which is our magnetic flux.
Yeah.
And our current, which is still our current. So if we look at this, what do we have?
Well, second finger, current, is going into the board.
Yeah.
Because of this X, that's what we know.
Luckily, Wayne's finger is already moving in the direction that our magnetic flux mostly is.
Yep, so it's going from
Field
north to south overall.
Yeah.
So that finger points from north to south.
That means the force is going directly down.
Absolutely. So we can go down this way. If it was quite a loose wire, then the motion would be down, it would move it down. But mostly it's just the force is going down.
But now we know what direction the force is going, we need to know how big it is, really.
Yeah, so for that we use an equation.
We do. So, Wayne mentioned a bit earlier that I think the magnetic flux is B.
B, that's what it will be in this equation, because that will affect the resultant force. If this is bigger, overall the force will be bigger. And it's measured in Tesla, and you can expect quite low values of Tesla, because Tesla itself is quite big.
Yeah. So, other things will affect what we have?
Well, the current going through the wire, if we up the current, we're going to up the motion, or the force.
Current, the length of the line?
Yep, and how long this wire is definitely going to affect it. In fact, the angle it cuts through this field is also going to affect it.
Now this is something that doesn't come up that often.
Yep, so we would say sine theta is going to affect it. So the angle it goes through.
But most of the time, and like here, it's in perpendicular to each other. So sine theta there will equal 1, so you can pretty much ignore it.
Yeah, exactly. So that's cool.
Yeah.
If it's going from north to the south, then it's at 0 degrees to the north-south field. So sine of 0 is 0, so the whole equation breaks down. There'll be no force if it's going in the same direction.
Yeah.
So what is the equation when we put all this rubbish together?
Well, Wayne's drawn it in one form in your top corner. That's how you often use it because you're often finding flux, but in this case we're going to find force. So this is how you find it in your formula book.
So F equals Bill sine theta.
Bill sine theta.
And as Trev said, you can mostly ignore the sine theta because it's nearly always at 90 degrees.
Nearly always, but occasionally they do things with stuff.
Yeah, so it's in your equation, in your formula booklet. And I'll draw that a little bit bigger. Rearranging this is often how you use it.
Yeah, so you're often finding out the magnetic flux. And then you might use it in a different place. Say we haven't got a wire perhaps we have a particle, so use a different equation there.
We do, so we're still working out the force on the particle as it
Mhm.
goes through things.
But because we're now doing particles, particles have charges, often.
They do, so B is still going to affect it,
Yeah,
but it now has a charge of that particle
yeah, and then this particle will move
with
How
a
fast?
velocity.
velocity, yeah.
Yep, so those are two new equations, and again, this actually does really have a sine theta on the end, but that never comes up in questions.
No.
So it's not like in your formula book that you just do this.
There is a nice example in the book.
No, but what we have done is found a real life example from a past paper.
Yep, and we've chosen one, question 3 from January 2011, so we thought, yeah, that one said the word flux somewhere.
And that's good, that's
and
what
that's
we're
what
teaching.
we're going for, so if you want to get up on whatever you're doing, you can look at it at the same time, but we'll explain every step so that you don't really need to.
Okay, so, are we ready to type in your password?
Nearly.
I'm learning your password.
I'll change it then. Alright, so question 3, we have a lovely diagram.
That's going to copy it.
That's a good plan. And it says, it shows part of an accelerator used to produce high-speed protons. The protons pass through an evacuated tube. This is shown in the felling of the paper. The path of the protons is this thing here.
Yeah, so I'm going to put P for protons just as a reminder.
Yep. It moves around the centre of the circle, so you have a radius there. It's a bit like circular motion in this case.
Yep.
And it says the protons are made to travel in the circle where radius R, with a magnetic flux essentially. B.
So there's going to be a B.
Yeah, the first question is using our left-hand rule, and that says take clear the direction of the magnetic flux density B that reduces the circular motion of the protons. So what you need to think about is what finger is magnetic flux?
Well, it's the field. It's your first finger. The field, the direction of the field.
Mm-hmm.
So,
Now,
do we know current and motion? Because if we do, we can work out that.
yeah. So first, I think always current is the easiest.
It is. So current goes in the way of positive charge.
Yeah. So if there's an electron in the opposite direction of the movement, but because it's the same, positive, it's
going
this way. So let's wait and put it there.
Yep.
We also have motion.
Yes. Now in this case, it might be confusing because essentially the motion's this direction. It's moving this direction.
Mm-hmm. But we're actually thinking about the force, and it's like circular motion, so it's all being pulled towards the centre.
So it's like that.
It's like that, which means our field is going towards you.
Yep. So our magnetic flux is going to punch you in the face.
Yeah, coming out of the paper perpendicularly.
Yep.
So that's part A.
So up, out the page. Out.
Out of the page, yeah,
Out the page.
not up the page.
No, not up the page, but up, out the page. That's
Yeah,
what
yeah,
I'm
just
going to put out page.
out the page perpendicularly. That's part A. That's easy. Left-hand rule sorted. So now it says show that the relationship between the velocity v of the protons and the radius r is given by v equals bqr over m, where q and m are the charge and mass of pressure respectively. Now this one we're going to combine a few things. We have one equation for f.
We do. We have F equals BQV.
Yeah, we're talking about particles now, so the charge of the particles.
And that's the difference between this one and the Bill sine theta.
Mhm.
Bill sine theta is for wires and stuff.
Yeah.
Because length of wire.
And then we have another one, which is what we use in circular motion a lot.
Yes, so it sort of thinks, can you look back to your old equation? So it might not have been your first move to look
Yeah.
back at previous exams.
So we're moving
You
around
need
in
to-
a circle, and we're talking about forces, we've got F equals mv squared over r. And now we're going to amalgamate them.
Yep, so we don't, there's no force in the resultant thing, so we just equate them.
Yeah, so they will be each other. That's fine. So BQV is equal to mv squared over r. Now we want v to be the subject.
Yep, so we rearrange this
Yeah.
whole thing.
So divide both sides by r and times both sides by r and divide both sides by v, sorry, and divide by m.
And we get v equals what it wants us to get.
Yeah, which is BQR over m, I think. Yes. And yes, shown that question, you just have to go, look,
Yep.
you know it's right, so that's okay. And then C is the last part we're actually finding. It says calculate the magnetic flux density B of the magnetic field needed to keep the protons in a circular motion of radius. So now we've got a value for that, 0.18 metres.
0.18 metres.
And the time for a complete circuit around our magical track is 2 times 10 to the minus 8.
Okay,
Yeah.
so
Pretty speedy.
what's it we wanted to work out?
You want to work out B.
B. So,
Yeah. So we want to use our BQV there, I think is the best one to use there.
yeah, it probably is.
So, V.
Yeah. I think what I would do is I would use this bottom one and rearrange it straight away. That would be my
Okay,
first step.
That works too.
I'd say B equals mv over qr. I would do that first.
Okay,
So
that's
rearrange
sensible.
this one.
But we don't know our V yet,
We don't.
but we do know the distance and the time.
We do indeed. So we can work out v because the distance is the radius, so we can work out what the whole circle would be.
Mm-hmm. So our S is the next question.
So speed equals distance over time. So that's pi d to
That's
work
our
out the
distance.
distance all the way around a circle,
Yeah.
which is 2 pi r, we have r.
Mm-hmm.
So it's just 2 times 0.18, which is 0.36
Yeah.
times pi, so 0.36 pi. That's our distance.
Yeah.
Speed equals distance over time, so
Yeah.
we do that distance to go all the way around one loop over the time it takes to do one loop, which is 2 times 10 to the 8.
And this gives us our speed, which is very quick, but that's what you expect, so that's
You
good.
expect it to be very quick in these questions, so
Yeah.
don't be thrown off by these sorts of things.
I'll write it just here, but we continue on.
Okay. So I'm going to rub these out now. That's lovely. So B equals mv over r. We've now worked out our v, which is 5.65 times 10
To the 7, sorry.
to the 7. So that's our v on the top. We know the charge of a proton.
We do, that's
1.6
1.6 times 10 to the minus 19. And the rest mass of the proton is in your book, and that has a different value.
Yep. So while you find that, we also know on the bottom the radius, because that's given to us in the question, is 0.18 metres. So then you need to put in the mass, which is something times 10 to the minus 27 or something like that. I'm sure it's just fine
Something
in
like
this
that.
book.
Ah, right.
So in the back of your formula book, it's got lots of things, and it says the rest mass of a proton.
Which is a little bit weird, because it's definitely not resting, is it? It's flying
going
around
pretty
high.
quick.
But we still use the rest mass, and that's 1.673 times 10 to the minus 27. Not very much, but protons aren't very big.
You type that into your calculator, and you'll get B.
You'll get B. It's not going to be a big number.
No,
I don't know what the number is then.
no, you haven't typed it in your calculator.
I haven't, because I was getting things, and the calculator's gone forever now.
Nice.
Thanks.
But that would give us a small value. You just type that into your calculator, and it will give you something.
Yeah.
So
I mean, the something is less important, really.
once you type that in, you'll
Once,
get a number.
yeah, but
That's the hard part.
And then part D is explain why the magnetic field does not change the speed of the protons.
And this is sort of a typical question.
Yeah.
It's always the same sort of answer for these sort of things, with things going in orbit around a force. You can say that the force is perpendicular. I'm going to put perp. Force is perpendicular. So no work is done. And that's literally all it wants you to say. And that's sort of typical of these sorts of questions. They always do that sort of thing. So the force is perpendicular to the actual motion. Remembering that the motion of the thumb, which we did, was actually the direction of the force, really. The actual motion you can see is round in a circle, because the force is perpendicular. Well, it's coming out this way. It's perpendicular. There's no work done.
Yeah, and now I typed other things in the calculator. The magnetic flux is 3.28.
So type that into your calculator and got the right answer. Well done, you.
Yeah.
3.28 Tesla, which is fair. It's a very. It seems like a small number, but it's supposed to be.
That's the kind of number you're expecting. And yeah, it's a well example.
So gangster signs are actually useful.
Yeah.
Well done.
Well done, youngsters. You're all New York.